Okay, so the next thing we want to learn how to compute is the arc length of a function that we're given. And so I'm going to give you the formula real quick, and then we'll sketch a picture for why it works. So for a curve given by traveling along one of these vector functions r of t for times t0 to t. We'll go ahead and do it like that. Doesn't really matter. The arc length is given by the integral. Oops. We're going to give it a name. We're going to call it S. We're going to say it's the integral when you go from t0 to t1 of the magnitude of r prime of t. And you're going to integrate that magnitude with respect to t. And another way you can write this is going to be the second line. You could say from t0 less than or equal to u less than or equal to t, the arc length at time t is s of t. Now you imagine that length we're calculating changes depending on how long we've been traveling along the curve. Integrate from t0 to t, magnitude, r prime of u, just some sort of placeholder, integrated with respect to u. These are obtained using the same formula. It's just sometimes if I wrote integral t0 to t magnitude dt, that would be abusive formula, and it can be confusing. So I've written it this other way if that's helpful to you for when you have to find it at an arbitrary value t. If this just confuses you more, stick to, this formula. You could probably figure it out if this last number wasn't given. And I told you I would sketch out kind of why this works. So let's go back to just any old picture of a curve. Let's call it that one right there, I guess. And we're saying that's going to be traveling along r of t. At every point on this curve, our r prime of t, we know, points like this. It's our little tangent vector. Kind of like that. Keep drawing it everywhere. And then if you go ahead and compute magnitude r prime of t, that's going to tell you the length of each of those vectors. And if you take an integral, you learned that's kind of like adding a bunch of stuff up. So what we're doing is we're starting from, your first time this happens at t0, your last time this happens at t1, and you're saying go along this whole thing and add all the lengths. So if you ever forget what this formula is, just what r means, what r prime means. I'm sure you could puzzle through it and make this formula work. So I'm just going to say this is a picture of how this formula works. And then we're going to do a quick example, just so that you can see the formula in practice. So we're going to find arc length of r given by 12t. I'll fix that. There's only so much handwriting you all should have to suffer through. 12t, 5 cosine t, and then 3 minus 5 sine t for 0 less than or equal to, well, it's actually written in the book, from t equals 0 to t equals 2. So it won't always be written in that less than or equal to form like I gave you the equation there. So all we're going to do is we're going to say, okay, you gave me r. I'm finding arc length. I know I need my derivative to do that. Derivative of 12t is 12. Derivative of 5 cosine t is minus 5 sine t. Derivative of 3 is 0. Derivative of minus 5 sine t is cosine t, holding on to the same sign as before. And then my magnitude is going to be the square root of the square of all the components, 12 squared plus minus 5 sine t squared plus minus 5 cosine t squared. So that's square root 144 plus 25 sine squared plus 25 cosine squared. Again, sine squared plus cosine squared is 1, so those 25s can combine. And I will get, apparently, 144 plus 25, is just 13. And so my arc length is s equal to the integral from 0 to 2 of magnitude r prime of t integrated with respect to t, integral from 0 to t of 13 dt, integral from 0 to 2, I just copied things down wrong between those two steps. So that's 13 times t from 0 to 2. That's 13 times 2 minus 13 times 0. That's 26. And so if we measured that curve given by this equation from plugging in t equals 0 to t equals 2, we would get that it is 26 units long. And that's how we compute